So today I will show you how classical thermodynamics consequence in microscopic and macroscopic scale. For the first, I will recommend you to watch these videos. You're done? Alright, let's get into it. In previous video, we learned about classical thermodynamics law, which is zeroth law, first law, second law, and third law. In this video, we will have special treatment for second and third law. If you recall definition of entropy in my entropy video, we will have that rate of change of entropy is equal to this, which when T approaches to 0, the rate of change of entropy collapses to 0. And ds non-heat here greater or equals to 0. And next, if we recall Clausius inequality theorem, we know that the loop counter integral of entropy is equals to 0, which means that the entropy itself is what we call state function. And then the next part, by this state function property, we have this equality of counter integral, which the right hand side is less or equals to 0, which equality coming when process is reversible. And notice that this delta Q here is about heat rate of change in the first law. Now comes the real problem. How we manage for many-body system, or especially too many-body system? Well, let's go to the next section. In many-body system, we can't measure one by one. I mean like how we measure one by one for too many body. Especially in particle, which is always in group or very large group, we can't measure volume, temperature, pressure, and other macroscopic one by one. Why? Because these three and the others of course is about macroscopic that measure something average in this group or collection of particles. And that's the crucial example. So to solve this problem, I mean we can measure one by one, so why don't we use statistics just like in my previous video, which here we use microscopic measure just like energy, number of particles, which then relate to omega or number of possibility of state. So then we get macroscopic measure just like entropy, temperature, volume, pressure, and etc. This concept is a key to the born of statistical mechanics in physics. But first, we need to really understand what is microstate and macrostate. Microstate is a measure that each particle has it one by one. For example, a particle can E1 energy and then E2 energy. Of course, here I mentioned about energy itself and then the number of particle, which is the only one particle called as one particle system. So it's microscopic. That here we have relation to all possible combination of microstate as omega or maybe as probability at I state or I level of state. Which next, macrostate is about summary of all microstate. I mean, we can measure it macroscopic easily, but not usually we can measure easily for microstate. For example, pressure, of course we need many body system, and then we have temperature, which is about kinetic of collection of particles in kinetic theory of gases, and then we have entropy and etc. In microscopic point of view, we can use this as constraint as I mentioned before. So here we have summary as total entropy, total energy, and the total probability, which in probability theory we know it's equals to 1. For example, in energy, we have total energy is about this summation, which epsilon I here is about energy I-leveled state particles, which means Pi here correspond to I-leveled state of that particle's probability. And by total probability is equals to 1, it means that total probability is about this sum, and of course this is equals to 1. That means all state in our system must happen, but not necessarily simultaneous. And here's the question. What about the total entropy? We know in previous video, we got two kinds of entropy, such this entropy that depend on omega, assuming that all particles in our system has equiprobability or known as Boltzmann entropy, and this one is maximum entropy at thermodynamics equilibrium. The next one is about Gibbs, which equals to this summation that in my video before, we know that Gibbs entropy less than or equals to Boltzmann entropy due to equiprobability made any particle can freely be anything, and this is not necessarily coexist in Gibbs entropy system. So here, relation between Gibbs and Boltzmann entropy is what we know about optimization. So we have journey from Gibbs to Boltzmann as optimization. And here we can optimize, but oh my god, we forgot about the constraint. For example, here I will use total energy constraint and probability constraint. Or for simplification, we have isolate many particle system. To optimize this entropy, we need to take the first partial derivative for each pi is equals to 0. But now with constraints such as this, which we know is about Lagrange multiplier method, and alpha beta here is about constant with respect to each pi. So by taking this differentiation, after we eliminate constant of integration, we get the result as this, and by modification between left-hand side and right-hand side, we get the next result as this, and then the final result as this. As I mentioned before, alpha beta is constant with respect to pi, but may depend on t, the energy itself, and etc. But did you notice something? Pi here is about probability. So, by plugging the probability constraint, we will have this equation, which here I define this expression as 1 over z capital or z partition function. So we get z partition function is about this equality, and then the final result, we have pi as this, which kp here is a Boltzmann constant. So we get the distribution for probability in isolate system. And now you may be thinking, until right now, we're using only probability. So what happens if we use number of particle in I state instead of probability pi? So in summary of my question is, what if omega has specific value, or I just can say, how if we use omega instead of probability? And the answer of this question, we have 3 different cases that commonly used in modern physics. The first case is Maxwell-Boltzmann. This case is about distribution of particle that has this property. First, the order of particle is important. So, each particle is distinguishable. I mean, we treat each particle as a different individuals. And the second, we don't care about degeneracy. So what I mean about degeneracy here, one EI, there are GI possibility that not necessary one. So here, the distribution of particles is about this omega, that is n capital or total particle number factorial divided by multiple multiplication for each nl factorial particle, and we multiply this quotient by this multiple multiplication for GL with power of NL, which means that each particle in L state has degeneracy as GL. So that's how tricky of degeneracy. The second one is Bose-Einstein. This distribution has this property. First, order doesn't has any means, or we don't care about order because this distribution relates to quantum particle that indistinguishable between particles if they have same state. And the second, degeneracy doesn't satisfy Pauli exclusion. And by this two property, we need combination for each state I. So the omega I is about this factorial with gi minus 1, that minus 1 itself come from one degeneracy lead to only one possible state. And by superposition in quantum theory, we can neglect any order. So we can divide with this, which you can see if gi is equals to 0, then this factorial, if you notice, doesn't have any sense or undefined just like in my gamma function video. And the last one here is about Fermi-Dirac. This distribution has this property. First, same as Bose-Einstein, which means we can neglect any order concern, but the second one, degeneracy satisfies Pauli exclusion, which means that one state restricted for one particle. So here, we treat the particle as vessel and the state or degeneracy itself as the particle. So each particle, we need to put one degeneracy of state and so on. By combination, we have omega I is about this, which is just combination, but now we're switching instead number of particles as the object, we treat the number particle as a vessel or configuration for gi. And as I mentioned before, these three is the basics in standard classic and quantum statistics in physics. And how to operate these three, I will give you some example in Maxwell-Boltzmann distribution. In And this omega, we can rewrite the omega as this multiplication. So we take too many particles as h and L approach to infinity, and then the number of all particles is about n capital, and the last one, this summation is about total energy E capital. In logarithm, we can see that omega will be like this, and by Stirling approximation, just like in my short video, we will get this result, and then by simplification, we have the next result as this. By this approximation and by Lagrange multiplier method as before, we get the result of first partial differentiation with respect to NL is about this, and next we can eliminate this fourth term because of subtraction, then the next result as this logarithm. This logarithm will lead us to this result. And by considering all the constraints we take, we will get this result, and this one is about Maxwell-Boltzmann distribution for classic particles. And then, with the same procedure for another such Bose-Einstein and Fermi-Dirac, we get Bose-Einstein as this distribution and Fermi-Dirac for this distribution. Bose-Einstein here for boson particles and Fermi-Dirac here for fermion particles. And that's how statistical physics or statistical mechanics in physics formulated. I hope you enjoyed this video. If you like this video, please share this video and give me some subscription by press the subscribe button below. If you have any question, please drop comment below. And that's it. See you later.